Afternoon. I noticed an interesting article in the paper recently um, about science. But I just read a bit of it, excerpts. In 1997, the Hungarian biochemist Katalin Karikó met another struggling researcher, the American immunologist Drew Weissman, as they queued to photocopy scientific papers at the University of Pennsylvania. Everyone know where the University of Pennsylvania is? Sorry? Oh, good. Okay. You know it's in Pennsylvania then. Okay. Well, there's I think that the Kansas State University or maybe it's the University of Kansas is not in Kansas. Okay. Yeah, right. But anyway, a lot of things to keep track of. After commiserating about the lack of funding for their work, the two scientists found a common scientific interest, the genetic molecule RNA, and decided to collaborate. This week, well, a week or two ago, their partnership achieved the apex of scientific recognition. Karikó, 68, and Weissman, 64, jointly won the $1 million Nobel Prize in Medicine for discoveries leading to the messenger RNA vaccines that stemmed the growing tide of coronavirus infection during the pandemic, saving many millions of lives and yielding sales worth $117 billion for the manufacturers, BioNTech, Pfizer, and Moderna. Okay. Oh, thank you. Okay. Over more than a decade of joint effort, the pair worked out how to manipulate mRNA, the molecule that translates genes into proteins, into a stable form that can be used in pharmaceutical and vaccine development. But while both scientists endured years of professional struggle on the way to the huge acclaim that greeted the success of mRNA vaccines against COVID-19, Karikó had to overcome greater setbacks than Weissman. In 2012, Weissman was promoted to full professor at Penn. The following year, Karikó was kicked out from Penn, forced to retire, as she told the Nobel organization after the prize was announced on Monday. The university told her that her work was not of faculty quality, she said in the 2020 interview. Okay, yet the scientist's commitment to her work did not falter. And so she somehow managed, she became vice president of research at BioNTech. They also had trouble publishing the work because it was the idea was so new. Eventually, the tide turned in favor of the mRNA approach pioneered by the duo in time for the rapid production of COVID vaccines in 2020, though not in time to save Karikó's academic career. Today, she has a position as an adjunct professor, and the university's leadership lavished praise on her when she attended Nobel celebrations there. In her Nobel interview, Karikó told female researchers, "You don't have to choose between having a family and science. Your child will watch you and follow the example you present." But Karikó's most frequently repeated message for scientists is about enjoying their work, regardless of any difficulties they may encounter. As the fizz flowed at Penn's Nobel party, she told her colleagues, I wish all of you to persevere and have fun. Do great things and don't give up that easy. Okay, so one thing that one sort of unifying theme for the course, I think that you could say, is AF algebras. The limits of finite dimensional algebras. A1, A2, so on. And if you have another sequence, B1, B2, so on. And then the idea is that if the K groups of the inductive limit are isomorphic as ordered groups, then this implies that the algebras are isomorphic. And so this shows that for the class of AF algebras, for the category of AF algebras, K0 is a what I like to think of as a classification function. You can't say it's just it's not labeling the isomorphism classes by a nice parameter, and certainly the isomorphism classes aren't countable, so you could just count them 1, 2, 3, and so on. Or now, if you look at the UHF algebras, we have I think some of you may be studying. I hope all of you take a look at it. The idea that not only are the algebras themselves, not only is there a canonical construction of UHF algebras, the Glim infinite tensor products of matrix algebra, she called uniformly hyperfinite. Not only is there a canonical construction which has parameter point in the Cantor set, because the supernatural numbers form a Cantor set in a natural way. Not only are not only is the data for constructing the algebras, so you have a one parameter family of these algebras parameterized by the Cantor set. Not only that, but they're all non-isomorphic. Okay, so you have they form representatives. These canonically constructed algebras form representatives for the isomorphism classes. So the just by automatically, because of that, the isomorphism classes are parameterized by this nice point in the Cantor set, which is a compact metric space. But in general, even for simple unital AF algebras, so the UHF algebras are simple and unital, but that's not why the isomorphism classes are nicely parameterized. That's just sort of a fact of nature, if you like. So even for simple unital AF algebras, isn't any nice parameter to describe the well, even the algebras themselves. I don't think you can say there's a nice parameter to describe the algebras. Like you have the supernatural number with UHF algebras. You had the category supernatural numbers mapping to UHF, right? You had a canonical construction, but there isn't any analogous thing known for any other class of AF algebras. But um, but there's a, it just happens if you look at the category of AF algebras, and then you look at it, exists another category. Now, if we look, say we look at stable AF algebras, AF tensor to compact operators, or the free float, or the free, in terms of the algebraic construction, free floaters. If it's free floaters, then you don't have to keep track of the unit because there's no unit. Right? Okay, so you just get ordered groups, certain ordered groups, and these very special class of ordered groups are called dimension groups, countable ordered groups, and there's a theorem. Well, every totally ordered group is included. Every countable totally ordered group is arises from some AF algebra, and there's a nice characterization of when the ordered group does arise from an AF algebra. Of course, since K0 preserves inductive limits, not only at the purely algebraic level, which is quite easy to prove with the idempotent definition, but also for C-star algebras too, because of some calculations that Klim worked out. Okay, but let's look at the purely algebraic setting. And then you have K0 A1 mapped into K0 A2 because it's a functor. Just keep on going, and because it preserves inductive limits, then that means the inductive limits are isomorphic. And so you can go to work on the isomorphism between the K0 groups. So they're not equal. It doesn't make sense to say they're equal, right? They're just you have two algebras, and inside each one you look at the idempotents, and also in matrix algebra, and you look at this notion of equivalence, which is maybe a little easier to understand for star idempotents, for self-adjoint idempotents. It could work perfectly well in that context. And then and then you take the isomorphism classes, the equivalence classes, so-called Murray-von Neumann equivalence, which apparently has a Toronto connection because an early graduate of this university was present from the beginning in some of the discussions between Murray and von Neumann as a graduate student. So, well, so you have two abstract constructions for two completely different algebras, okay? And so you get two semi-groups, and you get two, abelian groups, and which are ordered because of the semi-groups. You take the image of the positive elements to be the ones coming from the semi-group in the enveloping group. Well, okay, but these are just two groups just sitting in different rooms, maybe. You did one construction in one room and the other construction in the other room, and then someone just told you over Zoom that they were isomorphic as ordered group. Okay. Then somehow you're supposed to prove that the algebras are isomorphic. but it's not as if they're the same algebra. It's not as if the K0 groups are actually equal in some natural sense. And as in the case of UHF algebras, it makes sense to say the subgroups of Q are actually equal. So subgroups of Q containing the natural numbers in the unitary case, and you assume that they're equal. Okay, that's what the invariant is, and then you show that the supernatural numbers are equal, and therefore the algebras are equal because they're constructed from supernatural numbers. At least you don't. Well, up to isomorphism. But anyway, it's a very concrete approach. But in the general AF algebra situation, all you can do is just look at maps. Well, okay. And it just happens because of what the finite stage K0 groups are. It just happens that because the limits are isomorphic, you can intertwine the two sequences. Okay? And that's slightly that takes just a little work to trace that, right? But so if this is just a single, suppose A1 is just a single full matrix algebra, then this group is Z, right? It's with the positive cone Z plus. Z plus. Okay. And so what's the, in general, it's a finite direct sum, or ordered group direct sum. So what does intertwining mean? Well, intertwining means you want to map this group to, ideally, you'd like to map them just zigzag like this, okay? In a way that's commutative and in a way that's commutative, okay? And is compatible with the isomorphisms in the limit, because that's how you would get them, okay? But in fact, you can't do it quite such a simple way. You have to do it step by step. And you take the generator of Z, positive generator, and you follow that through to the limit. And then you look at it, what happens to it down here in the other abstract group, ordered group, okay? It's going to be some positive element in K0 of B. Well, what's the inductive limit? Well, the inductive limit, roughly speaking, it's things that come from finite stages, right? But you don't know which finite stage. So you get, so this one goes somewhere to here. Let's call it G prime. And then eventually it comes down here to, well, call it G. And it eventually comes down here to G prime, okay? So, and G prime is the image of some G double prime at the finite stage, okay? And you can, the first G prime that it's an image of may not even be positive. The first G double prime that the G prime is an image of may not even be positive, but if you follow it out by, if you look at what how inductive limits behave, if you go out farther, then you can choose the G double prime to be positive, okay? All right, so let's assume that it's positive and at some suitable finite state, okay? That you can choose it to be positive. Ivan, is that okay? Okay. Gerson, does that seem, is that okay so far? More or less okay. Charlie, is that more or less okay? Sorry? Well, it's an group, okay? So, yeah. So we're looking at certain order groups. And what the one abstract description of them, one characterization of which order groups you get, is you look at finite direct sums, ordered group direct sums of copies of Z, okay? And then you look at a sequence of such things with maps in that category, positive maps, positive additive maps, okay? And then you take the inductive limit, and that will be that will be that will come from some AF algebra. That's part of the proof. Okay, that it follows from the ideas in the proof. But that means then that that's one way of describing exactly which order groups you get. There are order group inductive limits of finite direct sums and copies of that. But then the F. Ross Handelman-Shen characterization is completely different. Okay, it's just general properties of a order group. Well, okay, so but this Z, group Z, it's generated by, has a single generator, and it's free. It's a free group, a free abelian group, right? So just as a group, there's a group map taking Z into K0B2 that takes the generator 1 into G double prime. Okay, so we can take the this one we can take down here, but then it extends well, and we want it to go to G double prime, but then it carries the whole Z along with it because there are no relations. Okay, there's nothing to say that if you map 1 down to here, then for any n maps into n times 1 maps into n times G double prime for n positive or negative number, right? So that's a map. So we have this map. Geez, there's I just broke the only long piece of chalk. Oh well, it's 2 pieces that are adequate. Okay, okay. So just have to be careful not to do it again. All right. So, but that's, and then the next step is just the same. Okay. You have to, again, you have to go from a single direct, a single copy of Z to finitely many, but that's, it's a free group, and you put the finite number of generators of each of the direct summands, and those have no relation, so you can map those into anything you want. It's like you have a vector space, and you have a basis, then you have any other vector space, and any family of vectors with the same labels as the basis vectors in the first space. There's a linear transformation which takes the basis vectors into the new vectors with the same labels, right? There's a linear transformation. It's unique. They exist. So that's the universal property of a free object, free structure. So okay, but that's how you get the intertwining. Okay, and the diagram is commutative because by construction, because at every stage, let's try and show that going down and up is the same as going across. Well, okay, actually this is a slightly subtle point. We're going to have to go farther out again. We're going to have to go farther out again because going down and going across all the way to infinity and going down, that's the same as going down and going across to infinity by construction, okay? And and then also going up here, the next stage, that's what we know is that that and going out to infinity is the same as going first to infinity and then up, okay? So if we go down and then up, at least if we then go all the way to infinity, then that's the same as going down and then across to infinity and then up, okay? But then going down was the same as going okay, you can see that I've got some work cut out for me, okay, to actually show that because this diagram won't be exactly commutative, we have to pass farther out, okay? We have to go farther out. And this is a good exercise. This is how I explain things, okay? It's like Samuel Beckett. Try, fail. try again, fail better. Okay, well, and maybe I'll pass the try again stage to you, okay? So, but don't worry, we're always going to come back to this. We'll come back to it until everyone is, well, maybe I hope they won't be tired of it, but I'm offering to come back to it often enough that everyone will be completely familiar with it, okay? Because this is the this is what has this is one of the things that has been a central idea in the subject for 50 years, okay? How's my arithmetic? It is 50 years. 1974, I announced this submitted talk at the ICM in Vancouver. So that's okay. So but the and that's step one. Remember the mnemonic for the proof. You have the we've just discussed the first zigzag argument, okay? Then there's the second zigzag argument, and that's the first zigzag argument is between the K0 groups. Is what we're talking about, the finite direct sums of copies of Z. And the second, I'll just do it here in case people can't see the blackboard. Okay, so so the second step is you can take each map individually and you lift it to a map between the algebras, okay? And these algebras are, we could take them to be the free-floating algebras over finite dimensional algebras, so we don't have to worry about units, okay? But definitely if it's a free-floating algebra over a single full matrix algebra, then any map at the K0 level between two such algebras comes from the map between the algebras, okay? So we don't have to worry about subsequences, don't have to worry about going farther out to do the second step. Then, but the trouble is it may still not be commutative. It'll be, so that we did go far enough out, we had to go to subsequences to get the first zigzag actually commutative at the level of ordered group, okay? And then, so we can, but if that's commutative at the level of ordered groups, we could hope that the liftings to the algebras are give you a commutative diagram. That would be compatible, right? That would make sense. But of course you can't do it because they're not unique. The lifting is not unique. Any inner automorphism composed with a particular map will inner automorphisms act trivially on K0, okay? If an invertible element and you conjugate by it, that's an automorphism of the algebra, and that will act trivially on K0 because any item potent will get taken into an equivalent one. There's a good exercise. Okay. So it would be, you know, if it happened that whenever you chose these maps, the algebra maps, lifting the K0 maps, if it happened that the map that the it just happened that the algebra map diagram was commutative, well, you'd have to pinch yourself, okay, because you'd be asleep, you'd be dreaming, okay. So and you would be able to tell. You'd be able to tell. I'm in the middle of a dream. Okay, that sometimes happens. I think that you catch yourself. Fortunately, before it's too late. Usually. Okay. Well, so in other words, you have to modify all these individual up-down maps. Unfortunately, even though it's lifting isn't unique and an inner automorphism, if you follow it by an inner automorphism, then you get instead of instead of this map, you compose it with an inner automorphism, then that's going to be another lifting. Well, if you just carefully replace each map, maybe you don't have to do it for the first one, but you change the second one, and then the third one, and so on. You change each map once by composing it with an inner automorphism. Then you still have that makes sense. You still have a bunch of algebra maps, which still lift the K0 situation. Which, I mean, at the end, I guess you want to have a strong isomorphism term, but the given isomorphism between the K0 groups actually arises from an isomorphism between the algebras. But the main purpose of making everything compatible with K0 is just so that you can apply the uniqueness theorem when you go down and up. When you go down and up, and at the level of K0, it's the same as going across. That means that going down and up, you can put in an inner automorphism after it to get the same as going across. And then the first triangle is commutative. Then you do the same for the second triangle, up and down. You change that up and down by inner automorphism to get the same as going across. And you notice that your purpose is to change the whole up down, but in fact you're only changing the down. That means you're not changing the up. The up is still the same. Well, if you had to just change it twice, that would be okay, I guess. But fortunately, the important thing is you only have to change each one finite number of times, I guess. But then all right, but that's okay. So that's how you get the third zigzag picture. It's just making the diagram of algebra maps commutative, and then you're in business. Okay, so you know, this would be a good essay topic, just to sort of sit down from scratch and work up the proof in your own words. It's called the Elliott intertwining argument, okay, which is a misnomer because Ola Bradley, as I noticed much later, Ola Bradley had exactly the same argument when he worked not with the K0 group of the algebra, but with the Bradley diagram of the algebra. Okay, and he had a notion of isomorphism with a functor. Well, he didn't do that. He didn't look at that systematically, but he had a complete proof that if you had two different AF algebras, and if the Bradley diagrams were equivalent in a certain way, then the algebras were isomorphic. And of course, the proof was this intertwining argument, okay? Word for word. It could put, you know, I'm not going to object if you put that into the essay instead, or put in a comparison, okay? And as a bonus, you could even take the category of Bradley diagrams and show that it's equivalent to the category of dimension groups. Okay, if you like the idea of doing elementary category theory. And let me just outline. Let me just review what is meant by equivalence of categories. Has everyone run into that notion? Okay. Now, usually you talk about functors in both directions, such that when you go forwards and backwards, and in some sense, it's like the identity functor, not equal to it necessarily, but naturally isomorphic to what's called naturally isomorphic to it. naturally equivalent to it. And actually isomorphic to it. That's a technical, slightly technical term. But and then also the backwards and forwards should be like the identity functor in the second category, up to a natural transformation. But it's there's an accepted notion of equivalence of categories which only involves a map in one direction. Okay, and that's what is easiest to show in the case of Bradley diagrams going to order groups. So the functor is quite very simple. You have a Bradley diagram. Did people, okay, thank you. Did people look up what how many countries what is often called Pascal's triangle popped up in over the millennia? Okay. I don't know if it came in. I don't know if it came up in India, but I wouldn't be surprised. Good, yeah. It's the most commonly known. There's an IBM chart of history of mathematics, which takes about the whole wall, about the size of two of these blackboards, and that's where I found out about this extended history of Pascal's triangle. They mentioned the Chinese origin, which was quite a few hundreds of years earlier than Pascal. Well, okay, so if you have a Bradley diagram, that's just a diagram. It's a schematic diagram, right? The information it has is for each row you have a certain number of points, and then for two adjacent rows you have a bunch of edges, okay? And if there's a question of multiplicity, then you put a number on the edge. So this is, if it's multiplicity 1, you don't have to put a number. If it's multiplicity 2, you can just draw 2 lines, or you can write a 2. But if it's 106, then you are supposed you want to write the number, okay, instead of the 106 lines, drawing 106 lines. And of course, if it's a googolplex, then you don't even want to write down the number, right? Well, you could just say googolplex. Yeah. I think that's how the well-known computer company, whatever kind of company it is, shows its name. Okay, so this is just a diagram, okay? A bit like a circuit diagram, for certain rules, and that you can, if you have a diagram like that, you can put in finite dimensional algebras at the different stages. One single full matrix algebra for each point, and then you can put in maps, which at least if you look at the free floating algebras, you put in maps. Otherwise, you have to worry about the unit going into the unit, or something that's too large to be the unit in the next place. If the multiplicity is 106, you can't write 1 by 1 matrices going into 2 by 2 matrices with multiplicity 106. But with the free floating algebras, you can do that. But well, okay. So that's one thing you can do with a Bradley diagram. You can turn it into a sequence of finite stage algebras, A1 to A2 to A3 and so on. With inductive limit, with some inductive limit, which is an AF algebra, and it'll be a general AF algebra. Conversely, if you have the algebras, the finite stage algebras, then you can uh, pull off a schematic diagram from it. Okay, so far so good. But suppose you want to just forget about algebras and look at the two categories of Bradley diagrams and of ordered groups. How do you go from one to the other? Well, to go from the Bradley diagram to the ordered group to the Bradley diagram, you have to make a choice. Okay, so that's um, but if you have the Bradley diagram, and to go from there to the uh, um, ordered group, it's just a functor. You just put a z everywhere. Okay, and then you notice that these numbers are all positive. The multiplicities, either single or zero edges or some finite number of edges. Those are all natural numbers, okay? And so that gives you positive maps from z into z. A single, well, any integer will give you a map from z to z, okay? But not necessarily taking positive numbers into positive numbers. But it just happens that the Bradley diagram with the positive numbers automatically gives you a map of finite direct sums of copies of the ordered group Z, which we just agreed a while ago is an arbitrary dimension group. So this is a functor. Well, you have to check that it takes maps between the Bradley diagrams in the sense of Bradley. So this could all go into a really lengthy essay, or you could edit it. You could edit the essay just to cover certain aspects of the theory. Okay, but that's oh, so what makes it a equivalence of what makes this functor an equivalence of categories? Well, so you have two categories and you have a map from one to the other functor. Well, the two objects, then the functor takes them into two objects on the other side. And what you want, and what you have is a whole lot of arrows in the upstairs in the left-hand category. Well, you want the functor to be a bijection on the arrows. You want it to exactly. You want the arrows on the right-hand side to correspond exactly to the arrows on the left. Okay. Well, that's that happens, and if every object arises, at least up to isomorphism, then that's one definition of equivalence of category. Okay, and that's why it's just an exercise to show that if you talk about the inductive limit of a Bradley diagram, I think that's a good way to do it. I mean, once you get the finite, once you put the z's in at all the finite stages, then you take the limit. Okay, that's a canonical construction. So that's the function. You have to check that it takes arrows into arrows for primitive composition, and then if you have that have two objects on the right-hand side, every arrow between them comes from, well, two objects that come from objects on the left. Up to isomorphism they have to. So you assume you have two objects that actually are the inductive limits of two different Bradley diagrams. Then look at the maps between the ordered groups. You want to show that they're in one-to-one correspondence with the maps between the Bradley diagrams. So this requires some homework, right? Because I haven't really gone into much detail what Bradley meant by a homomorphism between two Bradley diagrams, right? He didn't even call it that. In fact, he just looked at the isomorphism case and he called it an equivalence. Yeah. Well, okay. Well, no one objects to homework, I guess. That's supposed to be a joke. All right. Well, any questions?